Hello, everyone. As I was already introduced, my name is Jakub, and today I will tell you a little bit about patterns and practices for unit testing in Swift. The talk is based on the project that we have been developing for like 9 months, and it has a couple of things that we have learned during that time. The project is pretty big, and it relies pretty heavily on unit testing and test-driven development. I run my own blog. If you're interested in iOS development and digging deeper, then just come and say hi. You can also contact me via Twitter. There is the handle. And as you can see, I work for Alpassion. Before I start, there is one side note. I already did a test run of that presentation, and the feedback was that there is a lot of content packed in here, and it's pretty fast-paced. So don't try to read everything that's on the slides. Just try to focus on what I'm saying, and the slides will be available to download, so you can grab that later. And having said that, we can start. So the agenda for the talk is, first of all, I will introduce you to unit testing in general. I will say a couple of words about test-driven development, and also the reasons to use it or to not use this approach. Then I will later I will tell about engineering for testability, which is how to structure your code so that's easily testable. Then I will show you how to circumvent some of the common obstacles while testing, so testing view controllers and global functions. Then I will briefly tell about using sorcery for auto-generated test code, and then a couple of words about different metrics we use. So first of all, introduction to testing. So unit testing is just an automated piece of code that invokes a unit of work in our system and asserts whether it meets given criteria. And the unit of work is pretty crucial in here. You will learn why later. A good unit test must be automated, must run pretty fast, and it needs to be trustworthy, more than other traits of that. Because when the test fails, you need to know that it's the code that was broken, not that it randomly failed or whatever. And of course, it needs to be readable and maintainable. It's just the same code that you write for your source target. TDD, test-driven development, is like a Loch Ness monster of iOS development. Everybody knows about that. Nobody does that or seen that in a real project. And it's a programming technique that combines writing a test before writing just enough production code to fulfill the test. And from my experience, the typical response to TDD is that our team doesn't do that. We are not allowed to, or we don't have enough time, or it didn't work for us. And the first two of them, the first 2 points in there, I can share a pretty funny story with you. I used to work for a software development company, and we were subcontractors for a marketing agency. And one day they came to us and asked to rebuild the existing version of the code that we already had. And they wanted us specifically to estimate this as large as we can, because they wanted to sell the big product to their client and get a lot of money. So they asked us to just do whatever we want, just to have the best practices wherever. And we did the estimation, they bought it, we are doing that. And 3 months later, I come to the team which develops that, and I ask whether to do TDD or not. And the response is, no, we don't do that. We don't have time for it. So if it's not the ideal word, then what it is. And the third one is pretty important. It didn't work for us. If anyone has tried it and it didn't work, then this might indicate there was some problems with feedback loop. Maybe the code was compiling too slow, maybe the tests were hard to write, and this is what I try to show today, how to work around that. So the typical TDD workflow is just write a failing test, write a minimal amount of code to pass, this is the green phase, and then refactor. And that's commonly known, but something that's not that common is that TDD has 3 special laws that you need to obey to. So you can't write any production code until you write a test for that. And you cannot write more of a test than it is sufficient to fail. And not compiling is failing. That's pretty important. And the third one is that you cannot write more production code than it is sufficient to pass currently failing test. And for that, I will show a pretty quick demo. What I have in here is just a pretty basic view controller. It doesn't even work. It has one label in it. And I want to have a property called name that whenever you set this property, it will greet the user with the given name by printing it into the label, the special text. So what I would like to do is to have a property in here, but I'm already doing it wrong because I'm trying to write a production code before I've written a test. So I should go to the test target and try to write a failing test for that. So I'm doing that, and I just invoke the property in here. Now I should go ahead and write some assertion because I want to print it to hello label. But hey, this code is not compiling, which means that writing even more test code for that would violate the second law. So I cannot do that. I need to go back to the production code and make the code compile. So I need a property in here. And now it compiles. The test should pass. And I can proceed to write an assertion for that. I want the label that's there to display a text, hello Jacob. So I have written a test. I try to see whether it passes or not. Obviously, it doesn't. So now I need to write a minimal amount of code, a production code, for it to pass. I would rather like to have another assertion in here if I insert a different name, but that would violate the third law, which is I can't write any more of a test code than to make it fail, and it actually fails. So I need to write a production code right now, and it can be as simple as this. Okay, it's a label, definitely. Cool, it passes, but it doesn't work because it prints the same text every time. So now I need another test in here. I should probably write it down. So right now, everything compiles, and it would probably pass. So I need to write and keep writing the code until it actually fails. And it's a red test, so I need to write some more production code for that to work. And it's as simple as doing this. Oh, it's actually not, because the name is an optional. So I need to. Okay, so now I'm at the second step of TDD, and the third one is refactoring. So I can just change something about this code. I don't really like the if-let assignment, so I will just remove that using a map on an optional. Then I need to run the tests to check whether I have screwed something or not. Seems like I haven't, so I'm after the refactoring step. I can proceed to implementing wherever I want next. Okay, so this is how TDD actually looks like, but what it gives us. So according to the research, and this one is the most notable, it's done by the former employee of Microsoft, and they've compared 4 projects that were done in Microsoft and IBM against the 4 similar projects with similar requirements and complexity. One of the first group was all the code was written in TDD, and the other one it was not. They used other kinds of testing, but they didn't do test-driven development. And as you can see, the effort for writing TDD code was slightly bigger, from 15 to 35%, but the number of defects they found in the code that was pre-released were twice as large in a project that didn't use TDD. It just used another kind of development methods. So that's pretty huge. It's half better product, and I think that this research says that TDD is definitely worth it. And having said that, we should think about how we should write a code so that it's testable. And it turns out it's really simple. You just need to pass some values to functions and return value from a function. That's it. You have a pure function, like adding. And if you've got that pure function, then it's easy to test. You just pass a set of values, you assert the result, and that's it. Simple, isn't it? But it's not that simple in a production code, because actually there are this nasty word of side effects and so on. And there is this really great talk by Gary Bernhardt. It's in Ruby, but just don't be scared of. It's called Boundaries, and it sums up how you should structure your code so that it's testable. It shows that subsystems of your code should actually communicate using simple values, not complex objects or side effects. And I really recommend watching that. The point of this talk is that it divides the code into two parts. The imperative shell that has real-world dependencies, that does all the side effects, has stateful operations, and the functional core, which are the functions. They do all the decisions, so all the if and switch and guard statements should be in the functional core, and this functional core should only do purely functional transformations. And I wanted to show a quick demo. How does it look in a real code? I was looking for some kind of an inspiration for a short example for this talk, and I found it in my own code, unfortunately. This is it. This code is actually a scroll view delegate which makes the scrolling stop at the pages. So when user stops dragging the scroll view, it doesn't stop between the pages. It stops at the start of a page. And to implement that, you need a scroll view delegate, and you need scroll view with an end dragging method. And what's important for now, don't try to read through all this code, is that we receive a target content offset. This is a pointer to a point that scroll view should stop at. And if we mutate that pointer, we alter the stopping point of the scroll view. And what I've done in here initially is I've implemented the extension method on a scroll view, offset snap to page. It looks like that. There is a lot of code. You don't need to read everything. But what do you need to know is that it relies in some way of the state of the scroll view, because it takes frame and it takes content size in here, and it makes some kind of decisions. There are guard statements in here, for example. And this code is not immediately obvious that this code is really bad, but it's more obvious when you try to write a test for that. Because what happens is that you need to set up the scroll view, you need to maintain the frame, you need to maintain the content size, and you need to maintain this target content offset. So you need to mutate it before the test. You need to create a pointer for that, invoke this method, and then assert the mutation. So there are a lot of test cases in here. They require a lot of complex setup, and this is not what you want to do in your code. What you can do instead is try to move the code to another dependency that doesn't rely on a hidden state of the scroll view. So right now I pass all the arguments to that method with the width of the content and with the width of the frame, and I have a purely functional transformation. I pass all the inputs in, and I receive the target content out. And when I have rebuilt the tests, you can compare it, because Just give me a second. All those tests in here, like the three of them, are now replaced with this. So this is just a purely functional transformation. I just do 3 tests in one. It's really easy to set up. I just assert the values. And what's important, it's functional core, because I don't mutate the state right now. And to use that with the code of the delegate that we have, it's as easy as just having the dependency in there. And you can directly, you need a content info in here. This one is actually something specific, but you can see that I'm just using the content size in here and the frame size in here from the scroll view. This is what was previously hidden in an extension method. And now I replace the code with this. And this hasn't changed that much in here. But what it gave me is that when I were to test this class right now, I could only write 1 or 2 test cases that would make me sure that I'm passing the correct arguments to that calculator. And to test any other edge cases, I don't need to do this complex setup. I'm just using my functional core, and I'm testing that for everything. So this is why value types are so powerful. They make the tests really, really straightforward. And this approach is widely used, although not named again, in other appliances in iOS. So Redux-like architecture, view models, data bindings, they are all about eliminating stateful transformations and focusing on functional core, which is providing the data and changing the data. And this topic is pretty big and pretty deep. So I really recommend you watching a few presentations on that. Those are really quality ones, and you have a gist that has a reference to other talks about this topic. And I really recommend watching that, because it will give you a pretty nice idea how to structure your code. And if you are interested in the example I gave on my blog, there is exactly this example presented with all the references in there. So that was how to structure your code. The other problem is with testing controllers or with massive controllers. We all have them in our code, and it might be a problem. And to show that, let's try to find the largest files in our project. What will happen is that the output will likely look like this, unless you are doing MVVM or something different. But you have 8 largest files, and 6 of them are controllers. And what do you think? How big will they be? These are the biggest controllers in the app. So what should the numbers be? Give me a guess.
800.
Actually, it's the largest controller we have in our app. It's 140 lines, and it's pretty big. You can do smaller. But that's probably the way to handle the complexity of the controllers. And how can you do that? To check that, we need to examine the other metric, which is the average controller size. And if we would run that on the project we were working on, it turns out that we have 164 controllers in total, whether we can navigate to 38 screens in our app, which gives us more than 4 controllers per 1 screen. And those controllers contain like 12,000 lines of code in total. So if you divide that by the number of controllers, you will see that the average controller is 75 lines long. So the problem to solve in here is just add more view controllers. And how do you do that? You never subclass. It's a typical pattern, and you should never do that with controllers, unless it's a last resort or you really want to inherit all of the behaviors, but just try not to do that. Try not to build a big layer of dependencies by subclassing. Instead, add isolated child view controllers. And it's pretty easy to do. You create a protocol for a child controller, and those are the boundaries that needed to coordinate parent and child controller. Then, inside the parent, you refer to a child using the complex type, which is UI view controller and the protocol type. And then you inject a factory method into a parent controller. How does it look in practice? This is the code for adding a controller. It's what you will find in the docs of Apple. So you need to add a child, you need to add a view to the parent controller. You need to make it as big as the view that you intend to embed this in, and you need to call didMove with the parent controller in here. In this case, it's self because it's an extension on the controller. To remove the controller, you will do the same. You need to call the willMove method, passing nil parent view controller. You need to remove child view from the parent view, and then you remove the child from the parent view controller. You don't need to call didMove with nil parent view controller. It's not required. Then you create a protocol. In this case, we have a child controller that will handle the product selection logic, and it has only one callback. That is happen to be called when the product is selected. Then you implement that child controller. It has its own dependencies. It has its own implementation inside, and it exposes this protocol on the outside. In the parent controller, you take a factory as an input that creates this controller, and you simply embed that child inside the view where you need it to be displayed. This child controller is created with the factory that we have injected into parent. And what's beautiful about that, if you want to test that setup, you just create a child controller stub which looks exactly like that. So it's a controller that does nothing, and it has only this one single property exposed. And the test for parent controller is to create a child and to make the factory always return that stub child. And then you can test that whenever the child called this callback with a value, then this value will be displayed in the label that's contained in the parent controller. So you can test the boundaries between parent and child very easily. And the child view controllers are really, really useful for almost everything. And here are some overlooked examples. For example, buttons. They are great for using like a single button, a single controller per button. Because button usually performs side effects. They do error handling, and you need to disable interaction when something is going on. So the button is perfectly fine view controller and so on. Another example are forms, in which you can decouple the logic that actually transmits the value from the forms to your server using the API, and the logic for presentation or user input validation. It's typically really complex, so you can have this as a child and in a parent just do the networking calls and so on. And the third one is API data coordination. So imagine you have a parent controller, and it calls the API service to download the data. When you have this data, you need to make a decision. If the data is valid, you can display it in a child, which is immutable, so you inject the data in here. If the data is empty, you can create another child controller, which is immutable too, and it presents an empty state. And if you couldn't download that data, you will embed another child for error, and it's immutable. So you have the only mutable controller is the parent, which does only single API call. And you have 3 child controllers which are totally immutable. They don't do any logic, like any download logic on their own. And they are pretty easy to test then. OK, so another obstacle that we might face during the test-driven development is how to test global methods. Of course, you don't have global methods in your own code, or you shouldn't have that. But Apple does that, and we have to deal with that. Imagine you want a simple extension on UI image that produces the output with a given color. So it's the image colored with a single color. This is the implementation from our project, and we came up with this pretty easy helper for drawing the images. So it just takes a closure with context inside, and you can call whatever drawing methods on the context that you would like. To implement that helper, you need to resort to a lot of global UIKit methods, which are this and this and this very long method name that I couldn't even fit in the slide inside. And those, you cannot do anything about that. You cannot stop it, because it is what UIKit provides you with. And you still want to somehow test that without modifying this code heavily. So what can you do? To answer that, you need to know how Swift resolves the names. So if one day you will decide, just screw Apple, I will ship my own view controller, whatever happens. I implement a class named UI view controller, and I have my own set of methods in there, because I can. And if I try to instantiate that controller and invoke any method on that, it will compile and work perfectly fine. Because what Swift does, it knows this class is defined in your own module. So it is always prioritized compared to other imported classes from the external framework. Compared to that, when you would like to ship your own controller library, and you would import both your library and UIKit, this would result in a compilation error, because both controllers are imported, and Swift doesn't know which one do you refer to. And using that trick, sorry, using that trick, you can test global methods pretty easily. So what you do is create a method which has exactly the same name as in UIKit, and within that method, you should call a global stored variable, and this variable is a pointer to a method that actually does all the job. So you create that global variable, and you pass a pointer in here to the UI graphics get image to the original method from UIKit. And having that file inside your code, it will work exactly the same without modifying this. It will work exactly the same as without that, so as without doing that trick. But what's pretty neat about that is that when you want to test that, you can actually pass any closure to that stored global variable. And this way you can pretend that the global method returns completely other thing. You can create a stub in here and return it in the test always the same way. You need to remember to revert to the previous implementation, of course, in the teardown. And then you can easily test a code that uses global methods. Because in here, when you call drawing image, it will always return the same image as it is returned from this global closure that stores the work we are doing. So that's a pretty neat trick that we can use. So another thing we have learned that it's good to sometimes generate test code. And how bad it sounds, it's sometimes a pretty good idea. And to do that, you can use a sorcery. It's a tool that basically converts templates to the Swift code. And there are a couple of pre-made templates for you. One of them might be particularly useful for unit testing. And the problem it solves is equality check. So imagine you have an entity that's a simple model. You want to test how it's deserialized from JSON file. So what you do is you assert the properties one by one, and as long the smaller grows, and then you find yourself in a position where it has many properties and you forget to test another one. So we want to have an equality check so that the compiler will fail in here. But to have an equality check, you need to implement your own equals method, and that should be tested too. And it's pretty much an overhead because you are doing that for the test code only. Using a sorcery, you can automatically generate or synthesize the equatable implementation. So you take a template from the repository, you introduce a dummy protocol called auto-equatable, and make your entity conform to that protocol. And what sorcery will do before the compilation happens, it will generate a code like that for you. So it will actually perform the proper test of the equality, and that can be really useful for testing. Well, you might be familiar with the new version of Swift, for one, and it actually introduces the automatically synthesized equatable 2. So if you attach a equatable protocol conformance to your model, the code will be automatically generated for you. And how does it differ from Sorcery's auto-equatable? The biggest issue with that is that this automatic conformance cannot be declared as an extension. So you need to have that conformance when declaring the model, which is not quite what we want to do in that scope, because we don't really want to rely on that single model be equatable in the production code. We only want to test that inside our test target. So this is the only place we need this equality. And this is why Sorcery works better in this case for us. And we decided to keep this way, is that you can declare this in an extension. And this extension can reside in your test target only. Another pretty, let's say, funny trick is that with Sorcery is that when you write a lot of code that's created, a lot of view code or controller code that's created outside of interface builder, you will have a lot of these required initializers that do nothing. They return nil because you don't really use that. And if you don't really use that and you are looking at the code coverage statistics, you don't really want to see that this code is unused or untested, because it really pollutes the results. We just don't care. It's just pretty simple. It should return nil. And I don't want to flash. Don't want this to flash inside the code coverage results. And to fix that, you would have to test each initializer one by one, which is pretty bad. But you can also use Sorcery to do that. You don't have to go through that template carefully. But what it does, it actually creates an array of initializers that take a coder and return a view in here. And inside the template, we are iterating through all the views in here. And if the view contains initWithCoder method, we just append it to an array. What happens is that this is the output. So you have an array with all the initializers from all the views in your test target. And you can write a test that checks whether every initializer you have in the target, when you pass any instance of NSCoder, then it will return nil. And this is what you want to do, really, if you are not using Interface Builder. There are a couple more usages of Sorcery. You can use it for mock object generation. We don't really do that, but I know that the others do that, and it works good for their use case. So you might want to try that. You can also use Sorcery for some more complex assertions. For example, in our architecture, we have an enum. It's called root. And we want, for every case of that enum, to have a factory method in there. And if you forget to implement the factory method, then the code will crash, which is pretty bad, because this is how the architecture is structured. So we have written an automated test that from the Sorcery, we take amount of cases in there. And we just check whether we have enough numbers of factories in there. So you can do that with Sorcery too. And other than that, we have an integration test target. And in the integration test target, we are just calling the real API and checking whether it returns some results or not. And in that target, we are using Sorcery to check whether every request was actually integration tested or not. So you can have a lot of fun with that. You can generate a lot of code that otherwise, without metaprogramming capabilities, would be inaccessible in Swift. Last but not least, let's talk about some metrics that are pretty important when unit testing in general and doing TDD. So we measure a couple of them. First one is pretty simple. It's just the project size. So we want to know how many lines of code we have, how many files we have, or what's the average file size. And we want to check whether it doesn't grow too big. The second one is static analysis. We use SwiftLint, but this is what Swift devs are used to. But there is one pretty cool trick that we do. Actually, we use JavaScript copy-paste detector to automatically check whether we have any copy-pasted fragments of code along the code base. And I will present that later. And last but not least, the code coverage. It's pretty important when you're doing TDD or unit testing to know which code was not yet covered by the tests. All of these metrics are visualized using the Danger tool. Danger is a utility that is invoked during your CI build phase, and it gives you the output with linting the code request. So you get a comment, and in this comment you can define your own arbitrary rules that are broken in a certain pull request, like you have an edited README file or whatever. And this can do a lot more. We are using that to visualize those metrics that I have mentioned. So, coming back to this copy-paste detection problem. There is a tool. It's written in JavaScript, so you need npm to install that. And this tool is pretty scalable. And it supports a lot of languages. It supports Swift. It supports Kotlin, in fact. It supports Objective-C too, probably. I'm not sure, but I think it does. And using that tool, in conjunction with Danger, you can have that on every pull request. So whether anyone pushes a new version of the code, this tool automatically checks whether we have any duplications. And in here, we have found one clone. We have the exact file names in which this clone has happened. And we get exactly those lines in here that the duplication has detected. In order to configure that, you will need a configuration file for JSCPD itself. And it's the simple YAML file that looks like this. The important part is that it outputs all the result to a file stored in a disk. And then you can write a Danger method to automatically invoke that tool, and then you just take this file and try to parse it. It's just a simple JSON. So you extract all the duplications from there and just type down in the markdown all the issues that were found during the linting. This version of the script is really simplified. It doesn't do any error handling, or it doesn't check whether the file exists. It doesn't delete the file upon completion. The full version is located in here. So if you are interested into that, you can dig into those slides, and then you can visit this URL. It's all there. And our last favorite metric, code coverage. It's a percentage of the code that was invoked in the test. And while code coverage says nothing about the quality of the tests, which means that you can have 100% code coverage and don't do any assertions at all, which means your tests are useless. This is a pretty useful metric when you want to know whether you have any code that was not touched by the tests itself. And you can also visualize that pretty easily. There is a cool Danger plugin called Danger Xcov. It bridges Danger together with the built-in tool of Xcode, which actually measures the coverage. And if you download that and you import that to your project, then the output of that is just a simple command outlining you all the files that have been changed with the code coverage in here, like in the output. And having said that, since it's a last slide I have prepared for you, I wish that the next time we will meet each other, all of the projects you are doing will have this much coverage or higher. So I hope I will help with that. So thank you very much. If you are interested into something more or something deeper, then there is a list of additional resources that you can download and check. First, the slides from this talk. You can download it and go through them on your own. in a, let's say, slower pace. Then there is this great blog about TDD in general on iOS. I would really recommend. It's #1 resource for everything TDD related on in Swift development. And finally, this gist I have mentioned already, and this is actually the list of the articles and talks about the concept of imperative shell and functional core. And this is pretty deep. I would recommend to just take a look at that and try to understand the principle. Thank you.